Hello everyone, and welcome to this lecture about data science. Data science, new forms of data, new analytics, and new business opportunities. My name is Jeroen de Mast, and for the next hour or so, I will be your instructor. This is a seminar for IOTV, and at the start of IOTV, I am delivering this lecture from my living room, which happens to be in Amsterdam. So welcome. I invite you to join me and see what we will be talking about. Data science in industry, that is my field. I'm the academic director of data science for industry at JATS. JATS is the Euronymous Academy of Data Science, the graduate school on data science of the universities of Eindhoven and Tilburg. I am also scientific director at Holland Innovative, and lastly, I'm a professor of statistics and data science at the University of Waterloo, which is in Canada. Who are we? Well, I can imagine that you are an entrepreneur, a professional, a manager, maybe a student with an interest in innovation. And innovation is pretty much what we will be talking about, innovation with data science in industry. Let's first clarify a bit what the word data science means. If you look it up on the internet, you'll actually find a lot of definitions of the word data science. It's a relatively new field. That means that we are still in the process of figuring out what it's all about. But something that is common to most definitions of data science is that it's a multidisciplinary field. It's a field that combines various other fields. One definition that personally I like a lot is this one, where data science is defined as the combination of data analytics, data engineering, and data entrepreneurship. Another way to explain a bit what data science is and what it does is by telling you a bit what various data science professionals, what they do. So you'll see two professionals here, a data engineer and a data analyst. Data engineers are professionals who focus on the IT side of data science, the computer science side. So data engineers are professionals who know a lot about databases, data warehousing systems. They are professionals who know how to build a data pipeline. And they have a lot of expertise in big data storage and computing solutions, cloud solutions. Data analysts, on the other hand, are people who have their expertise more in machine learning, in statistics, in analytics. They know how to explore data, do data mining. They are the ones who build models and algorithms. They are versed in creating useful visualizations of data, build dashboards. What then is a data scientist? Well, a data scientist is a more senior position, and it's a more multidisciplinary position. Data scientists know a lot about the IT side of data science. They know a lot about databases, about data pipelines, but they also have a lot of expertise in data analytics. They master machine learning. They are trained in using statistics and building statistical models. But the data scientist is even more than that. Data scientists are also business savvy. They know how to translate business problems and business opportunities into data science problems. And also the other way around. Data scientists know how to recognize the business value in data and in analytics. Data scientists are also senior project managers. They know how to manage data science projects. They know how to deliver and deploy results. Essentially, and in general, they know how to get things done in possibly large and complex organizations. Well, this lecture is about data science in industry. And in this lecture, first I want to show you some examples of how data science is applied in industry and what type of applications they are and what the impact is of those applications to what's going on in industry, how industry is developing. Also, I want to tell you a bit about what's new. What's new in data science? What do we do differently now compared to, say, 10, 20 years ago? And so that's the bit about new forms of data, new analytics, and new business opportunities. And finally, I also want to show you a bit how data science works. So you will probably hear a lot of talking about machine learning, AI, algorithms, analytics. I want to show you a bit what it is that all of these techniques do, how they work. Let's start at the beginning. Let's start with talking a bit about some typical applications of data science in industry. It may come as a bit of a surprise to you, but actually the most common applications of data science in industry are in HR analytics and in marketing. Honestly, though, that is not so much my field. My field is more about manufacturing, product development, the technological side of industry. That's mainly what I will be talking about. So if you think about data science application in industry, they range from data science used to control production processes more efficiently, also data science to improve product designs, data science to augment products with data-driven services, offering smart products maybe driven by AI. And lastly, and the most revolutionary, data science as a basis for entirely new business models for companies. Of course, there's a gradation in these categories that I mentioned here, ranging roughly from incremental innovation driven by data science to more disruptive innovations. We certainly need to talk about that. But first, let's make it a bit more tangible. I want to give you a few examples. So here's the first example. It's a rather typical application of data science in industry, and the purpose is to make production processes and supply chain processes more efficient. The example is from the fashion industry, but you'll see similar application in many other industries as well. So what's the idea here? Basically, the idea is to analyze sales statistics, but also blog posts, social media. The idea is to analyze that sort of data science, and based on those data, try to forecast what demand will be and try to identify trends. Because if you can forecast demand, if you can identify trends, you can use that information to adjust your production mix and to adjust your logistics. What's the business value in that? Why would you want to do that? Well, if you can make accurate forecasts of what demand will be, you may be able to approach the holy grail of operations management and supply chain management, which is to deliver the right products at the right time, in the right volume, at the right place. A nice example of how powerful this type of data science applications can be is an example that's mentioned a lot in the industry. It's an example that involves Beyoncé. At one point, Beyoncé performed during the opening concert of her tour in a dress that made a big impression. How do we know? Well, social media were all over this new dress. And interestingly, a company called Zara, they monitored what was going on social media, and they picked up on this trend. They picked up on all this talking about this dress that Beyonce wore at the opening. So they identified a new trend and they responded. They responded by designing an entirely new product line inspired by Beyonce's dress. And they manufactured it. They shipped it to retailers and they managed to do all of that within 6 weeks. Within 6 weeks of the opening concert, the new line of fashion was available in retailers all over the world. 6 weeks. 10, 20 years ago, that would be considered quite an accomplishment. Let's talk about another example. This example is in consumer electronics. This is a company who sells about 40,000 products worldwide. And essentially what they want to do is to build an issue detection system, early detection system. And so if somewhere in the world there's an issue, a quality issue, a perception issue with one of these 40,000 products that they sell, they want to detect that issue as fast as possible. Because the sooner you detect an issue, the more adequate you can respond. Response could mean anything based on what the issue turns out to be. Possible response could be that they stop shipments. Another response could be that maybe they flush the supply chain of bad parts, if that turns out to be the issue. But the essence of it is that they want to detect issues as fast as possible. Now, one source of data that you could use to detect issues is data that you probably have in-house. Data about reclaims, warranty data. Also, you could try to analyze complaints. However, this company believes that there's a richer form of data available, namely reviews that are posted by consumers on online retailers. So think about websites of Amazon, Coolblue in the Netherlands. On these websites, consumers will post reviews of the products that they buy. And of course, you should take reviews with a grain of salt, but it's a very detail-rich source of information. And the idea was that by analyzing these reviews, these texts that people write there, that could be a rich source of information that could reveal the fingerprints of an issue. And the idea is that it helps us to detect issues sooner. Some other examples of data science used in industry to make production processes more efficient is systems that quickly detect impending equipment failures, or data science used to optimize maintenance, making it more efficient, or forecast demand, and on the basis of demand forecasts, align supply and demand. Now, one new thing that these two examples illustrate is the one about new forms of data. If you think about data, see a more traditional form of data here. This is a data table. We have a number of variables that we measure, and we have a number of data points. That's the traditional form of data. So your data, for example, in your reclaimed database will probably pretty much look similar in form to this one. Nowadays, we are in the era of big data. And the two examples that I just discussed are examples of that. So what is big data? Well, big data is different from traditional forms of data in 3 ways, the 3 V's they call it. The first that comes to mind if you think about big data is probably data volume. And we go from megabytes to gigabytes to terabytes to petabytes. But a bigger revolution, that there's also a change in data velocity. In the old days, we would have a given data set, we could analyze it, we could draw some conclusions, and that's what they call batch-wise data analytics. One step upwards is to do periodic, for example, once a day to make an analysis of your data. But nowadays, if we think about big data, we're thinking about analytics that happen real time. And we are no longer talking about data sets, we're talking about data streams. When Zara is monitoring social media, it's monitoring blog posts. That's not a batch process. That is real-time, continuous monitoring of data sources. Maybe the biggest change is in data variety. What you see here is the traditional form of data. It's a data table, in which you have columns and rows. One step upwards is a database, for example, a relational database like a SQL database. But nowadays, data comes in a large number of different forms. Also, photos are data. We can use the photos to do analytics, to make predictions. Documents, websites, we can scrape websites and take information from there. For example, the consumer electronics manufacturer, they will get their data from online retailers. And that means that they are scraping websites to get their data. Also, the data there is not a table of numbers, it's text, it's natural language. So also the variety of forms of what data means has developed from tables of numbers to a large number of sources of information and data. Here is a third example of an application of data science in industry. This example is from a manufacturer of high capex equipment. And essentially what they want to do is to identify the factors that affect the equipment's lifespan. So this is an application in reliability engineering. And the idea behind it is that if you identify factors affecting the equipment's useful life, you can use that information for making the product designs more durable, more reliable. Of course, this sort of applications is not new in itself. This is essentially the field of reliability engineering. What's new is that traditionally, that sort of applications were driven by reliability tests, by experiments, stress tests, accelerated life tests, that sort of experiments. And that sort of tests are still very important because experiments are still the best way to establish causal effects. However, nowadays, there's also other sources of information that we can use to supplement what we learn from experiments. Nowadays, a lot of equipment is linked onto the internet, and that means that we can monitor systems in the field and get a lot of usage data from them. So we can collect data about how equipment in the field is used, for what sort of tasks. And we can collect data about loads. We can collect data even about environmental conditions. And given the enormous amounts of data that we can collect that way, that is actually a very rich source of information that we use to supplement the information that we can get from the more traditional reliability experiments. So I have shown you now 3 examples. 2 were examples where data science is used to control production processes more efficiently. The last example is an example where data science is used to improve product designs. Now let's turn to the more revolutionary applications of data science in industry, namely data science to augment products with data-driven services to make products smarter, and the one that is most disruptive, data science as a basis for entirely new business models for companies. This is a simple example of how you can use analytics and data to create essentially a new value proposition for an old product. The product here are tires, not very high tech. But what this manufacturer has done, they have built sensors into the tires. That's attractive because nowadays sensors are very cheap. And they measure many physical characteristics of the tires. And based on that, they can monitor the condition of tires. And based on this condition monitoring, they can predict to the user the optimal moment to replace the tires. What's the business value of that? Well, it's quite attractive for customers because if you can predict the optimal time to replace the tires, that minimizes vehicle downtime and it also minimizes premature replacements. You find the optimal balance between the two. Other typical examples of the use of data analytics and data to augment products is a lot of new products that you see now, for example, smarter MRI scanners, smarter cars that are driven by AI features. For example, AI-driven image recognition. Then let's turn to probably the most revolutionary application of data science in industry, where data and analytics are the basis of an entirely new business model for a company. And the example here is about a car manufacturer who tries to sell insurances. Most car manufacturers at this moment are developing that sort of services. But let's see what's going on and what the thinking behind that sort of applications are. The thinking is, one line of thought is that in many industries, technological knowledge is quickly becoming a commodity. Consumer electronics, that's something that has already happened. It's quite difficult at the moment to make profit in consumer electronics in the West. But it's happening in many industries. Technological knowledge in many industries is quickly becoming a commodity. And that means that the more traditional business models, where manufacturers design products and then manufacture them, that's basically how they make money. That sort of business models is under pressure. And as a consequence, manufacturers are exploring new business models. And this is an example of that. The new business model here is that the car manufacturer still designs and manufactures cars, but also tries to sell additional services. The thinking here is that if you manufacture cars, you can equip them with a lot of sensors. And these sensors, they can measure where a car is driven, how a car is driven, when a car is driven. That creates a lot of information that traditional insurance companies cannot collect. So it creates a competitive advantage for car manufacturers. The traditional insurance companies, the data that they have available is some basic information about the driver and the car, age, experience, condition of the car. But a car manufacturer can collect more data. And this additional data that a car manufacturer can collect represents business value. It puts car manufacturers maybe in a better position to offer insurance products, to offer more attractive insurance products than traditional insurance companies. So the business model then may be something like pay how you drive. And rather than offering insurance products based on a fixed per month premium, you can offer an insurance product based on a pay per mile system. This sort of new business models, many of which are driven by data or by analytics, they call that servitization, where manufacturers are exploring new value propositions, new business models, where they try to sell services in addition to the hardware products that they sell. Also think about, for example, products where they, rather than selling you the car, try to sell you a lease contract. And the lease contract offers a lot of services like maintenance, like finance. That's called servitization. So many examples of how data science is applied in industry. And you'll see the gradation here. Incremental innovation is data science used to make current products more efficient or to improve current product lines. The next step is data science as a basis for new value propositions for current products and making your current products more attractive by adding data-driven features. And the most innovative one, data science as a basis for entirely new business model, like car manufacturers selling insurances and that sort of service products. So you see a gradation here from incremental innovations to disruptive innovations. Or as they call it in innovation management, Horizon 1 applications versus Horizon 3 innovations. Horizon 1 innovations are applications of data science for the current horizon, our current product lines. Whereas Horizon 3 is about creating opportunities that may become more actual beyond the current horizon. So this is basically the model that I have in mind. Innovation on 3 horizons. And innovative companies should think about all 3 horizons. That's the main point of this model. And so the first horizon is incremental innovation. It's about innovating about data science applications that improve the quality, reliability, and efficiency of current product lines. So that's applications where the focus is on efficiency, on exploitation, we call it in business. Traditional forms of analytics like Six Sigma, for example, they focus on that type of innovation, Horizon 1 innovation. Horizon 3 innovation is disruptive innovation. It's about what will happen after the current horizon. It's about creating options for future businesses. It's about new business models. The focus there is on exploration, exploring new opportunities. It's about learning. In between is Horizon 2. Horizon 2 is about rapid scaling. Those new business models that seem to work, and the next step then is to rapidly scale them and develop them into a mature business. So in Horizon 2 applications, the focus is on growth. Now, my main point here is if you think about applying data science in an industry, in an industrial company, it's important that you think about all 3 horizons. It's important not to restrict data science applications to only Horizon 1. Usually, I recommend executives to create an innovation roadmap. And this innovation roadmap essentially is the plan for how we will innovate and improve current products and current markets. That's the first horizon. But it will also make a plan for the next products and markets, Horizon 2. And it will also have the initiatives and the efforts to create new options for the future, Horizon 3. So an innovation roadmap typically spans 10 years. And by creating a roadmap, it allows us to manage conflicts between the 3 horizons. For example, it allows us to think about a good balance of effort. McKinsey, for example, they talk about the 70-20-10 rule, which basically says that you should invest about 70% of your resources in innovating Horizon 1, the current products, current product lines, about 20% in the next products, and about 10% of your resources in these exploratory products that try to develop new opportunities for the far future. And this is an example of an innovation roadmap. Note how indeed it spans 10 years, the first 3 years, 5 years from now, and 10 years from now. And look at how Facebook, in this case, is exploring their current products. Bear in mind, this example from a few years ago, so they're a few years ahead now. But you'll see the current products here, next products that they are developing in the second horizon, and opportunities that they are developing for the future on the third horizon. Well, let's take a moment to recapitulate what we've seen so far. So I have illustrated how one of the things that's new in data science in the last, let's say, 10 years or so, is that we have learned to use new forms of data. Totally different volumes, from megabytes to, sorry for that, to gigabytes, to terabytes, and to petabytes. But I think the biggest revolution is in the variety of forms of data, where nowadays also natural language could be data, photos, images could be data, social media could be data, documents could be data, websites could be data, etc., etc. And where nowadays the emphasis is not so much on analyzing fixed data sets every once in a while, but instead we are dealing now with data streams that we need to analyze real time. I've also highlighted new business opportunities. I compare to more traditional applications of analytics, such as Six Sigma, reliability, operations research. The focus used to be on Horizon 1 applications, where we use data and analytics to improve current products and product lines, the traditional form of product development, for example, where data science, data and analytics are also driving the more disruptive types of innovation that we call Horizon 3, where companies are exploring entirely new business models. The example about a car manufacturing that is developing insurance services, an entirely new business model for that sort of companies. And it's driven by data and analytics. Well, in the second half of this seminar, I want to show you a bit what data science, what is new forms of analytics, what they do. What's machine learning? What is artificial intelligence? What do they do? How can you use them? So let's turn to the next section. New analytics, machine learning, artificial intelligence, algorithms, data mining. What is it that all these techniques do? Now, this is the sort of traditional analytics, statistics, whatever you call it, that I am guessing most of you will be somewhat familiar with. If you took a statistics course somewhere in school, in university, you'll recognize it. It's a sort of analytics where we use maximum likelihood estimation, regression analysis, analysis of variance, driven by p-values. Typical for these sort of analytics is emphasis on causal models. And recently, these more traditional models, we've also learned that they have limitations, especially for the new forms of data that we have discussed. These new forms of data, big data, they have in common that they are what we call high dimensional. High dimensional means that we have data sets where we have many columns. We measure many variables. And as it turns out, the more traditional forms of analytics, regression analysis, ANOVA, analysis driven by p-value, it doesn't work that well. It's problematic. These algorithms, they often fail to converge, for example. The last couple of decades, they have witnessed the invention of a lot of new forms of techniques, new analytical techniques. You see a few of the most popular ones mentioned here. So in addition to what we are used to, least squares regression, we have different types of regression analysis now. We have, for example, techniques that are called regularized regression. One particular form that's very popular is lasso regression, for example. We have techniques with colorful names like random forests, random forest classifiers, random forest regression. There's a whole range of techniques that's called support vector machines, and there's neural networks, etc., etc., etc. The last 2 decades or so actually saw a very large number of new techniques in statistics and machine learning and statistical learning. And what many of these new techniques have in common is that they fit models that essentially are quite similar to the more traditional models, regression models. The main difference is that they are far more complex. They are what they call non-parametric models, which basically means that there are models with many parameters, very complex models. And as a consequence, they require massive computation power. Well, actually, for a modern laptop, that's not really an issue, but it's a sort of computation power that 30 years ago was unheard of. And these new analytics, they work well with high-dimensional data. They work well with big data. They can work with these new forms of data, natural language, pictures, images, social media structures, etc., etc. So you see a very simple data set here. This is not big data. This is a very simple data set here. One X variable and one Y variable. And then in the more traditional analysis techniques, we could fit a third-order polynomial, a cubic regression model. And essentially, we're fitting then 1, 2, 3 parameters. Give you a little bit of a feeling of what these new analytics do, I have fitted here a so-called random forest model. And a random forest model is actually the average of a large number of simpler models. So these simpler models are called regression trees. And each of these regression trees here has about 50 parameters. The random forest model is the average of 100 of those regression trees. That means that the random forest model has about 5,000 parameters. The 4 parameters that you see here. And so these models are far more complex. Neural network models, they can easily have hundreds of thousands of parameters or even millions of parameters. Now, the names of many of these new techniques, they are quite colorful. Support vector machines, neural networks, random forests. However, what all of these techniques do is pretty much the same thing. Namely, all of these techniques, they model relationships between X variables and Y variables. And these relationships, there are 2 types of them. In the old days, we would emphasize causal models. We would model the cause and effect relationships between the axes, which we would call the causes or the influence factors, and the effects, the Y variables. And the idea was that our regression models would at least be a good approximation to the true causal mechanism that we try to model. What's typical of many of these more modern analytics techniques is that they are not so much about causal modeling, Rather, they are predictive models, which means that they do not claim that they represent the causal mechanisms. They only claim that they are good predictors. So now the X variables are rather called predictors, and the Y variables are called responses. And since we are not claiming that these algorithms, these models, that they capture the causal mechanisms, these models tend to be what I call black boxes. Also, in view of the complexity of these models, thousands of parameters, millions of parameters, it's typical for these models that they are very difficult, actually impossible often, to interpret. They're black boxes. And they're machines, they're prediction machines. If you give the X values as an input, they will give the Y values an output, and that's basically it. It's difficult to interpret what the model means. The prediction machines. So the essence of a lot of what goes on in machine learning and data science is to think about problems in terms of X and Y variables. The Y variables in statistics, we used to call them dependent variables or response variables. In machine learning, they call them labels. And the Y variables, that is the characteristics that we want to predict, or that we want to explain, or that we want to optimize. You see in this example, the Y variables are caffeine percentage. So apparently this example is about the manufacturing of decaf coffee. And the second Y variable is the cycle time. So this is a batch process. And the batch cycle time is one of the two variables that we want to predict or explain or optimize. And the point of machine learning and statistics is to identify the relationships with X variables. In statistics, they call them the independent variables or the influence factors or the explanatory variables. In machine learning, they call them features or attributes or predictor variables. And the X variables are the characteristics that we want to use to predict or explain or optimize the Y variables. In this example, you'll see a lot of characteristics of the production process, like some characteristics of the coffee beans and the moisture. For example, the raw caffeine percentage is another one, the origin of the coffee beans. But you'll also see some X variable that look like process settings, like a soak time and an extraction time. And the idea then is that these X's, we hope that they are good predictors for the cycle time and the caffeine percentage. Now that means that in order to be able to apply machine learning or statistics or statistical learning algorithms, we need to do a translation, because usually business problems or business opportunities are not presented in the form of X and Y variables. And the skill to translate a business problem into the form of a question about X and Y variables, that is one of the essential skills that data scientists need to learn. So you see a lot of text here. And that is a description of the business opportunity here in terms of storytelling. And you may read that indeed this is a project at a manufacturer of coffee, and that indeed we are talking about decaf coffee. And you'll also read that in order for decaf, it's important, of course, caffeine percentage isn't too high. As a matter of fact, decaf should be below 0.1%. And you also may read here that the whole purpose of this project is to reduce the batch cycle time. But of course, at the same time, the caffeine percentages should still be acceptable. Now, let's see if we can make the translation from this description of the project's purposes in a lot of text, as storytelling, into a data science problem. So what you see here is the translation in terms of y variables. Apparently there are two y variables that we want to predict, optimize, explain here. One is the batch cycle time. And the goal here is the lower the better. If we can reduce the batch cycle time, then we can increase the production capacity, which may give us more revenues, and thereby improving our return on assets. There's also a second y variable, which is the caffeine percentage. And for the caffeine percentage, we have an upper specification limit, which is 0.1%. This is decaf, and food laws simply state that if you want to sell decaf, the caffeine percentage should be below 0.1%. So it's a quality issue. And if we fail to meet this requirement, we'll incur cost of poor quality, which has a negative effect on the return on assets. So by doing so, we have modeled the relationship between the y variable, which is the focal point of the data science project here, and we have demonstrated what is the relationship for business KPIs. What's the business value of this project? And then what we try to do in the machine learning project is to model the relationship between our y variables and some x variables, which are properties of the coffee beans and a number of process settings. And that is the general form of data science problems. And they are always about y variables, and we can show the business value that's implied by these y variables, which answers the question, why is this project important? And in the data science project, we are looking for the x variables, which are the characteristics that we want to use to predict or optimize or explain the y variables. So in the end, this is the data set that we need to collect. And we need to collect data about the y variables and the x variables. And that is basically what all of these machine learning and new statistics techniques, what they do. I'll explain a few more terms that they use. You see here the terms regression and classification. That is one way to discriminate between a lot of these machine learning algorithms. They talk about regression techniques when the y variable is a continuous characteristic, a numerical characteristic, such as cycle time and caffeine percentages. There, the y variables are numbers, and it's the reason why they call this a regression technique. Whereas a classification technique has a y variable that is categorical. This example, for example, it's whether the batch of coffee beans has been rejected or passes quality control. Here the y variable is not a number, it's two words, either reject or pass, and consequently, this is a classification model. So basically what all of these machine learning techniques and AI techniques, what they do is they model the relationship between x and y variables. And they do so on the basis of a historical data set. So you need a data set. That means that you need to have data about a large number of batches of coffee for which you have data about the x variables and you have data about the y variables. And based on these data, we can fit a model. Machine learning, they talk about you train a model. They call this supervised learning. And once we have fitted the model or the algorithm or the classifier or whatever you call it, then we can apply the model. And the application of the model is that for a new batch of coffee beans, if we measure the x variables, then based on them, we can predict the y variables. And we can do so because we have trained an algorithm, we have fitted a model based on historical data. Let's go over an example. And I invite you to challenge yourself whether you got it. So we see a data set here where again we have a few properties of coffee beans and like their bean size, the porosity of the coffee beans, etc., etc. We also see the origin of the coffee beans. And what we're trying to do here is design an algorithm that can tell the origin of the coffee beans, that's this column, from the other properties of coffee beans. So the first question here is, what are the x variables in this example, and what are the y variables? Give it some seconds to think about it. And I hope that you have found that the x variables here are these properties of coffee beans that we want to use as a predictor. And the characteristic that we are trying to predict is the origin of the coffee beans. That's what we are trying to do. And notice that I'm using the word prediction, but prediction doesn't necessarily mean that we're trying to predict something in the future. The word prediction is used for everything that we try to tell, like here the origin of coffee beans, which is actually not in the future. It's their origin, so that's something from the past. But even then, it's called prediction. The next question is, what sort of a model is this? Is this a causal explanatory model, or is this a predictive model? A few seconds to think about it again. I hope that you guessed that this is a predictive model. Here we are not claiming that the origin of the coffee bean is caused by all of these characteristics. Think about it, doesn't make sense. The only thing that we're claiming here is that we can predict the origin of coffee beans from these characteristics. And the last question here is, what sort of technique is this? Is this a regression technique or is this a classification technique? Well, the distinction between regression techniques and classification techniques is in the type of y variable. The y variable here is not numerical, it's not numbers, it's categorical, it's words. It's Asia or South America or Africa. So that means that the y variable that we're trying to predict here is categorical. And by definition, that means that what we're trying to do here is a classification model. Now, I want to show you two other types of machine learning techniques. The first one is a range of a class of machine learning techniques that are called unsupervised learning. The example that we just discussed is the opposite. It's supervised learning. And supervised learning means that we are fitting a model based on a data set in which we have data about the x variables and the y variables that we're trying to predict. Differently, we have data available where we know the correct answer, we know the true origin of the batches of coffee in the data set. And based on that sort of data sets, what we can do is basically what I just showed you is to fit a classification model, for example. So a classifier could work as follows, for example. You could fit a classification model like a regression tree, which first maybe looks at the bulk density. And if the bulk density is large, then the algorithm will classify the beans as being from South America. If the bulk density is smaller, then the algorithm may observe the bean size and based on the bean size, classify the coffee as either being of African origin or of Asian origin. That's a classification algorithm. So what would unsupervised learning look like? Well, in unsupervised learning, we have data about the x variables only. So we don't know the y variables. And that means that we cannot train a classification algorithm, as in this case. So what can we do? Well, basically, what the data look like if you're trying to do unsupervised learning is that you can make a similar plot, but in this case, we don't know the correct answers. We don't know the true origins of coffee beans. Supervised learning, we don't know the y variables. What you try to do in unsupervised learning is you try to identify patterns, salient patterns, patterns that stand out. And the pattern that stands out here is that the data look like they are clustered. You may see that there's 3 clusters. And once we've identified these clusters, then maybe our domain knowledge may tell us what the nature of these clusters is, and that may tell us that these clusters could correspond to the origins of coffee beans. What's the value of that sort of an exercise? Well, by doing so, we may have identified another potentially interesting characteristic, like the origin of coffee. And that is basically the idea of unsupervised learning. It's an exploratory technique where you try to identify new, potentially interesting characteristics, actual y variables, by identifying salient patterns in the data, such as clusters in this case. Now, besides supervised and unsupervised learning, there's a last class of techniques that I want to show you what they do so that you understand a bit how they could be useful. And that's a class of machine learning techniques that's called deep learning. Well, the name sounds intriguing, deep learning. However, bear in mind that in essence, also deep learning algorithms are still trying to do the same thing. They're still trying to model relationships between x and y variables. In essence, pretty close still to regression analysis models. What's the difference? What does shallow learning mean, and what does deep learning mean? Well, the more traditional algorithms in statistics and machine learning, like random forests, like least squares regression, like support vector machines, they need a historical data set that's already in this form. So it's a table where we have columns corresponding to x variables and y variables. Often, however, the raw data are not yet in that form. For example, if your raw data is natural language, or if your raw data are images, an image is not a series of columns with numbers in it. And then the more traditional way to do it is that you use domain expertise in order to identify in, let's say, an image, for example, what the relevant features are. And that's called feature engineering. And so you require an expert on image analysis, for example, to identify edges, and then make the translation of an image to the location of the edges, and maybe use these coordinates of the edges as the numbers that you can put in your data sets. Now, in 2012, they discovered in machine learning convolutional neural networks, which is an architecture for deep learning that has that's been quite successful in some applications. And what these deep learning techniques can do is that they can learn automatically to identify the relevant features, the x variables, so to say, in your raw data. So where in traditional machine learning techniques you use domain expertise, the idea in deep learning is that the algorithm can learn to identify the relevant features, the relevant x variables, automatically. And they do that by actually making a whole stack of models. So it's not a single model between that captures the relationship between X and Y variables. It's a whole stack of models. It's in layers, and that's where the name deep learning originates from. To give you a little bit of an impression of how that could work, let's see a typical application of deep learning, which is an image recognition. And there's a handful of very successful applications of deep learning. Image recognition is one of them. Natural language processing is another typical success story for deep learning. This example, however, is about image recognition. And what the algorithm that we're trying to train here is a model that can recognize people from pictures. And so the idea is that we train the model to do the following task. If we show a new picture of a person, the idea is that the model will then recognize the person who is depicted on the picture. So the model will then tell us, oh, this is Alice. Note that essentially this is the same thing. This is supervised learning. This is in effect a classification model. It's a classifier because the Y variable that we're trying to predict is categorical. So it's a classification technique that we're using here. Now, let's see how this translates to the story about X variables. The input for the model are pictures, but what the model actually sees, of course, are the pixel values. Digital images have pixels, and every pixel has a pixel value, or typically 3 pixel values. And they are numbers, and it's the raw data. But think about it, this raw data is a lot of data. It's high dimensional because in a typical picture you have a lot of pixels. So you will have a lot of pixel values for each of your images. Now, what you nicely see illustrated here is these layers of models that you use in deep learning, where the models in the lower layer, they learn to identify relevant features. Typically for images, relevant features are edges. And in the next layer, they discover more high-level features. So they may discover the locations or the form of a nose, of eyes, of a mouth. And only on the highest level features will they look at the entirety of a face. And so this nicely illustrates what I just explained. In the traditional shallow learning models, you need a domain expert to make the translation from your raw data, your raw pixel values, to, for example, coordinates or the forms of facial features. The impressive feat of deep learning is that you can train a layer of neural networks to identify these lower level features automatically. So I'm slowly heading my way towards the conclusion of this seminar. We have talked about new forms of data. We've talked about new business opportunities, Horizon 3 applications of data science in particular. I hope I have managed to give you a bit of a flavor of an impression of how all these statistics and machine learning algorithms, what they do, how it works. As a conclusion to this seminar, I want to talk a bit about what you should do with all this information. And the point of the departure is a situation that you may have found yourself in, where you are reading about all these new technologies, like digital twins, like AI, like process mining, deep learning, Internet of Things, etc., etc. And then maybe people are talking to you and they say, oh, you really should do deep learning. Deep learning is the future. You should do Internet of Things. Internet of Things is the future. Well, that sort of thinking, where you take technology as the point of departure, I find that problematic. because I think if you adopt new technology only driven by the story that it's the future, that you should do it, then you are driven by FOMO. You are driven by fear of missing out. And FOMO is not a good basis to adopt these new technologies. So let me, as a conclusion of the seminar, offer you a different line of thinking. For me, all these new technologies, they are but hammers, they are tools, they are only techniques. And if you take the attractiveness or the hype around new tool as a point of departure, well, the problem is that if all of these are just hammers, all of your challenges are nails. And so I believe you shouldn't take new technology, new techniques as a point of departure. You should start with the nails, not with the hammers. So the line of thinking that I suggest is to start with business opportunities that you recognize in your business. And you've seen in my examples how I try to model business opportunities. In data science, typical opportunities require some data sources. We will do some analytics, and there should be some business value in it. That would always be my first question. What is the business value? What is the business opportunity? What is the business problem that you're trying to solve? And my next question will typically be, what is the underlying strategy? Where do you want to be in 5 or 10 years from now? What is your innovation roadmap? What sort of business models are you trying to develop for the future? And the next question will be the translation of a business opportunity, of a business problem maybe, into a question about X and Y variables. You have seen me demonstrate how to do that. And only then, as the very last step, once you have translated your question into a form that involves X and Y variables, only then should you think about finding the right tools. And maybe for some problems, you need cutting-edge, state-of-the-art, complex tools like deep learning, like a convolutional neural network, for example. However, my guess is that for the big majority of the opportunities that you see, it's much better to use a simpler tool, like a traditional statistics model or a more traditional machine learning model like random forests. My guess is that for the vast majority of the applications that you might consider, the simpler tools will do. That is basically the end of my story for today. Thank you for bearing with me for this hour. Thank you for sharing this passion for data science and data science application and industry with me. If you want to learn more, well, of course, you can find a lot of information on the internet about data science and data science application in industry. I want to highlight 3 propositions that you may consider. In May, we start with a 4-day course, which is called Data Science for Six Sigma Green Belts and Black Belts. As the name suggests, it's a course targeted at people who already have a strong background in analytics, since they are a Six Sigma Green Belt or a Six Sigma Black Belt. The purpose of this course is to introduce in 4 days' time some of these newer techniques from machine learning to your skill set. In November 2020 at Yachts, we start with this program. That's the fully fledged program called Data Science for Smart Industry. It's an 18-day program targeted at professionals working in industry, so that's engineers, Six Sigma Black Belts, maybe even managers working in industry. It's a rather complete program. 18 days, we run the program in Den Bosch, And the objective of this program is to train the next generation of data scientists in industry. And lastly, data science, part of it are technical questions about machine learning, about data engineering, but much of it, as I believe I have demonstrated in this hour, is also business questions. For one, it's about an innovation strategy, creating an innovation roadmap, but it's also about how to manage data science. What sort of an organizational infrastructure do you need in order for data scientists to be able to do their jobs? And how should you lead the transition to becoming a more data-driven organization? For that sort of purposes, we offer executive workshops where we work with a management team or a group of managers and executives in shaping an innovation strategy for their company, and where we also try to create this organizational infrastructure that organizations need in order to apply data science effectively. Well, thank you for your attention. This is the end of my lecture. Hoping to meet you at some point in real life.